This is the fourth seminar of our seminar series this spring, and consistent with the theme of the seminar, we be addressing, large loads and the impact on the grid. And we have an excellent speaker, Mark Lauby, who will be presenting this. He's the senior vice president with NERC. Now, I want to read his bio, and is very impressive. He joined NERC in January 2007 and has held several positions, including VP and Director of Standards and Vice President, Director of Reliability Assessment and Performance Analysis. Prior to NERC, Mr. Lauby worked for EPRI for 20 years, and that's where we met and worked with him for many years. And began his industry career in 1979 at the Mid-Continent Area Power Pool in Minneapolis, Minnesota. In 2012, Mr. Lauby was elected to the North American Energy Standards Board and was appointed to the Department of Energy's Advisory Committee by the Secretary of Energy in 2014. He served as a chair and a life member of the International Electricity Research Exchange and served as chair of a number of IEEE working groups. From 1999 to 2007, Mr. Lauby was an appointed member of the Board of Excellent Energy International Company Limited, an energy service company based in Thailand. He's been recognized for his technical achievements in many associations, including the 1992 IEEE Walter Fee Young Engineer of the Year Award. He was named a fellow by IEEE in November 2011 for leadership in the development and application of techniques for bulk power system reliability. He was awarded the IEEE Power and Energy Society's Roy Billington Power System Reliability Award. In 2020, the National Academy of Engineering elected Mr. Lauby as a member, citing the development and application of techniques for electric grid reliability analysis. He's also a member of the IEEE Power and Energy Society Advisory Committee focused on providing strategic support to PSE Board of Directors. He's the author of more than 250 technical papers, expert systems, transmission system planning, and power system and numerical techniques. He earned his bachelor's and master's degrees in electrical engineering from the University of Minnesota. In addition, Mr. Lauby attended the London Business School Accelerated Development Program, as well as Executive Leadership Program at Harvard Business School. And without further ado, I'm going to introduce Mark. Mark, the floor is yours.
Thank you. Thank you. And just a thumbs up. You can hear me?
Yes, we can hear you.
Fantastic. And you can see my slide.
There we go. I think I've got my mic unmuted. Good to see you, Mark.
Hey, how you doing, Jim? Good to see you as well. I was going to wear my Columbia shirt today, but I didn't.
There you go.
Heading off to DC on a workshop on large loads. Yeah, looking forward to it. Yeah, thank you. It's good to see you.
Good to see you as well.
So Jim knows all this, just so you know. So I'll go through some of the history here, how we got here. I think it's always important to understand kind of the lay of the land. And many of you remember the 1965 blackout. I know Jim does, probably Rudy does, maybe some of you do, but it was a kind of a shock to the electric power industry because there was a lot of benefits that were being gathered through interconnecting different power companies to each other. You know, we're weird that way in the United States, where we don't just have one power company like EDF for France or National Grid, which is a transmission, but it used to be CGB, but rather a pile of different companies and co-ops and municipals for a variety of reasons that those companies were formed and to provide energy and electricity to the public. And so the blackout kind of paid this idea that though there are huge benefits of interconnecting, that one in sharing frequency, and therefore, exciting, the transformers at the same frequency, And you could then, of course, take generating units that go up to creating, at a 60 hertz level, and using magnetics, and then using magnetics to transform from low voltage to high voltage, because a alternating current, creates a voltage change and currents, and then transporting it long distance and then transforming it back down to load. Huge benefits there. There's also risks, and the risks really come to light when you have certain events where something happens on your system and it impacts your neighbor, or vice versa, and you don't even know what they're doing. They may not be designing the system to the same level. They may not be coordinating well with you, sharing information well. And so in 65, when this blackout occurred, a number of leaders within the industry, including Canada, got together and said, how can we solve this problem? If you just had a US solution, well, that really wouldn't go well in Canada, because the Canadians, of course, don't like us telling them what to do anymore. We like them telling us what to do. And so the idea of forming an organization, a nonprofit at the time, initially it was called the National Electric Reliability Corporation, but then the North American, and then finally, then of course, or Council, a North American Council, and then finally a corporation later on. And this really kind of pulled together, by the way, at the same year, as Rudy indicated, EPRI was formed. But how do we do research together? How do we collaborate to identify and address reliability impacts on the system, via distribution systems, consumers, nuclear, thermal, whatever? So these two organizations kind of went off from 68 going forward, and they've had kind of an evolving pattern. You'll see in the 70s, of course, the economy of scales and large generating plants. And the question is, can we build them fast enough because the growth of the system? But then it started slowing down in the 80s. There was a kind of an anti-gas movement. We couldn't use gas for electricity until about 87. We used gas for heating and all that because we had a finite amount of gas. And I'll more on that in a second. And in the 90s, of course, is when we started reflecting on maybe developing markets. And it was kind of set off by CEGB in the UK, where they sold their stuff. It was a federally owned organization that basically provided electricity all the way down to the distribution consumer. They sold it off in bits, but they kept the transmission together and the system operator together. And then that kind of started winding across the world. In certain parts where electricity prices were high, the question is, can we get more efficiency through markets? And that also then created a conundrum, which is, who owns reliability? If there is a problem on the system, was it the generator's fault, the transmission company's fault, the distribution company's fault, or the load did it themselves? Who is responsible for what parts of reliability? And that's when there was a discussion that started in the latter part of the 90s around maybe organizing an organization that would set standards that everybody had to follow, and make sure that they followed those standards, and have a compliance regime. And then the 2003 blackout occurred, and that really was an exciting time for the discussion of reliability. They already had some proposals on the table, and the Power Act of 2005 called for the formation of an electric reliability organization. In this case, NERC filed for that and was accepted. And that organization is to set standards, make sure that they're followed with a compliance and enforcement regime. So it's kind of like a regulator, but we also have Canada, and it's regulation that is written by industry. Industry writes the standards they're going to follow and votes on them. It's very much a kind of an American standards approach, right? 2/3 majority, bring it to our board signs off on it, sends it to FERC. And then there's also an engineering group, which is what I support. And that group really kind of does a number of things. They gather data on the performance of the system. How does the transmission work, and how's the generation work. And of course, GADS has been around a long time, generation of availability data system. I remember calling Ron Nebo in 1980 to get that data, but then also a transmission type data set on performance and also for misoperations and a host of other things. We've had to expand to get into solar and wind. But again, what's going on in the system? What can we learn about emerging risks? What do we do to mitigate those risks? And then we do engineering studies, and of course we do a forecast. And I'll never forget in 2007 when I joined NERC, I was asked to write the long-term reliability assessment. That's our 10-year look ahead. We just recently released one here, looking 10 years ahead. And in that report, I said we would have to build a pile of new coal plants because we were going to run out of gas. Conventional gas was gone, and there was no technology that on the table for us to access the other gas that was there. And then fracking came along and changed the whole thing. Now, of course, we do have a lot of gas. We just don't have ways. Sometimes we don't have ways to transport it because we don't have pipelines, but that's another. So it's like trying to build a transmission. It's very hard. So anyway, we want to kind of give an evolution of the industry in the U.S., especially because it's kind of unusual. Co-ops being formed because they were going to support farmlands to electrify farms because there was no money to be made for it from an investor-owned. And municipals that got tired of investor-owned, perhaps with higher prices, felt like they should run their own system. So we had this kind of grouping of federal agencies that were there to manage flooding, be it the TVA, which is the Tennessee River and Chattanooga River, or the Missouri River would be WAPA, Bonneville, that does the Columbia River. And then, of course, then generating power as a result of managing this flood water. So it's kind of an unusual grouping of utilities that we have. And they all work together because reliability is critically important to their DNA, to make sure the consumer has access as much as possible to certain levels. Obviously, you can't build for every possibility and way too expensive, but what is the level of reliability? What is an adequate level of reliability? Of course, I think some of that's changing over time as more and more things get electrified. So that kind of gives you an idea of NERC. If I can get this to move forward. Okay. I think I kind of really went through this, which is our mission to assure the effective and efficient reduction of risks to the reliability and security of North American bulk power system. And we've, tackled a number of things here recently, and I'll talk about them a little bit later on as far as emerging risks. And then we can talk a little bit about large loads, which are, again, one of those things that have come out of nowhere over the last 2 years, and it's something that's really significant and something we need to deal with. Assess the current and future reliability, look forward, make sure we're ahead of things, not looking through a rearview mirror. It's one of those things, and those of you may have heard me in front of FERC. Nobody ever calls you at 3 o'clock in the morning and says you did a great job. They only call you at 3 o'clock in the morning when your relay didn't work right or something didn't work right. So that's kind of the situation we're in with the power industry. Analyze events, see what we can learn from them. So kind of faint signals sometimes called, or used to be called the bird in the coal mine, canary in the coal mine, but I guess we don't have coal mines anymore. I don't know. Active participation by all our stakeholders, including regulators, state regulators, federal regulators will come to our meetings, as well as co-ops and municipals and investor-owned, and of course our Canadian colleagues also come to help us identify and mitigate risk because they're running into the same things. Maybe not so much in cold weather because they know how to run stuff in cold weather in Canada, but in some parts, some other things too. And of course, we're accountable to the FERC. We submit our standards to them. We have to submit our budget to them. The consumer pays our bills. Basically, you pay 28 cents a year, covers the reliability regime. And of course, Canadians, they are accountable to the National Electricity Board, not the FERC. So just kind of get an idea of I think I actually went through this already with you, so I'm not going to go through that again. Let's see if I missed anything. I missed the hurricanes. Oh, I did miss that in 1980. I started in business, 79. I could have put that in here. And then 2007, of course, I joined NERC. This all kind of fundamentally comes down to this trilemma and how we measure the implications of a good resilient utility. And you have these three legs, and this is not new. I think the IEA has an index around kind of this trilemma of access and affordable energy, making sure it's reliable and secure and resilient, I'd say as well. That's the resilient grid, but also resilience for a consumer. Resilience is really how long you're out, right? And then environmental sustainability. How do you balance these three legs? And we think to a certain extent we might have kind of tilted this a little bit recently toward more of the environmental sustainability. And the problem you run into is that you start running into costs in other areas. Maybe it'll be less reliable, or the prices go up. So again, it's always been a continual kind of balance. So we actually do pretty well in the United States and in North America, of course, with the Canadians and all the hydro. They do very well compared to some other countries, but it's still a continual balancing act. So, we have this kind of risk environment that we're dealing with, and it's really changing. It's dramatically changing. And, for all the years that I worked in the power industry, I've never seen change like this. Not bad, just different. And it calls into question a lot of the rules of thumb that we have. Rules of thumb that came to us from engineers back in the 60s and even the 50s. And I'll say 1947. But this rapid resource mix change, where we're going from spinning mass with hot water, boiled by some fuel or another, to a computer chip, a solar panel with inverters. And how do we make that transition? And how does that change the way in which we develop the controls for that system? How do we manage the controls of that system? And folks have maybe heard me talk about this before, with a tall building. You've ever been to the new Freedom Center or in Taiwan, I think it's 441 or it is a didn't like fours. It must be another number. But if you go up to the top, you'll see this huge ball. And it's got shock absorbers on it. And that ball is a mass of control, and it controls the swaying of the building due to any kind of perturbations, earthquake, wind. And if you start taking now mass out of that ball, you start losing your ability to control that building. And it's a similar type of thing that we have going on with our grid. We are spinning a lot of mass, and be it through water or which I guess you don't boil, hydro, or nuclear or coal or gas. And now we're going to more of I call it a computer. And you can do that, but you need to be mindful of what you're doing when you're changing that grid. And how do you substitute some of the characteristics of that mass with something else? Batteries, synchronous condensers, how do you manage oscillations, power damping on the inverters? A lot of things that one can do, but nobody is doing currently. So again, these are one of the challenges. And then, of course, the tools that we have are the rules of thumb. One is single-phase model. Well, inverters, maybe you need to have three-phase models. And that means that we need to make sure that we're training undergraduate engineers in three-phase models, not just single-phase modeling, because they come out of school and they know how to do load flow, and not necessarily EMTP, right? Or some tool like that. Another, of course, is the extreme weather, especially because our resources now are more and more dependent on weather. So what we need to understand then is what is the implications of that. An example, 60,000 megawatts of capacity in the midsection of the country, from let's say Saskatchewan to Texas, generating 200 megawatts because it just wasn't windy in the midsection of the country for about 24 hours. We have to manage those kinds of situations, and cold weather would also bring into the URI impacts and the interplay between gas and electric systems. And I dare say that's another interconnection, is the gas and the electric system. But what happens on one system impacts the other. They are dependent on electricity to winterize and to run their compressors and to run their processing plants. And we're dependent on the gas to run our power plants. So there's an interdependency there. So extreme weather has become much more of it. Hi, Andrew. One that we need to start thinking about, how do we manage that? We have been writing standards for winterization, for example, for power plants. We used to do that with our cars in Minneapolis, but I guess they have to do that with power plants too. And then wind implications. Florida, for example, the state has hardened its grid to a higher level. So we need to kind of keep that in mind, because these cold weather spells, we just had one here a couple of weeks ago. We really had to watch that one and what were the implications of it and where our standards working. And for example, battery storage was huge in Texas because they lost some wellheads they froze them off, and they couldn't get the gas out of them, but they were able to substitute with a substantial amount of storage, electric storage. So again, they have to design the system and operate the system a little bit differently. Of course, the growth, and this goes to the large load issue, but even without large loads, transportation electrification, that's not going to go away. It may slow down, depending on who's running the show, but it's not going to go away. Because these technologies are people like them. I don't know, we've been in an electric car. I think they're cool. You can do all sorts of stuff. But again, I think that the public will be also using electricity more in their homes, in their factories, as we bring in and reindustrialize the United States, bring back some of the factory work that's being done in other countries, and just that kind of growth. And we're projecting in the next 10 years a growth of 250,000 megawatts in the United States. Now, that's 25% in the next 10 years. That's a lot of megawatts, and how we're going to get there. And also, see, the other thing that I didn't mention before is that this is no longer a capacity problem. Another rule of thumb goes out the window. 1 in 10 was a calculation that we did to say, if we can build a system so that basically on peak, one event in 10 years will occur, and it was a probabilistic analysis, then we had a system that we could hand to the operator, and they had plenty of reserve margin to run that system through thick and thin. We have now decided and realized that this is now an energy problem. The capacity gave us energy plus essential reliability services, voltage, frequency, mass, inertia, or frequency support, gives all that. But now we have to study those pieces separately. We don't just get generating capacity of 400 megawatt units going to give you 400 megawatts. 400 megawatt unit may give you 100 megawatts or 20, depending on what's going on outside. So now another rule of thumb: 1 in 10 is gone, and single phase modeling is gone. We have to start thinking about energy, expected unserved energy, 3-phase modeling. And of course, the toxic soup of cybersecurity and physical security challenges. And that continues to, evolve across the world. And we don't even know what we have baked in our system. We have certain SIP standards. We try to develop a perimeter around areas to remain secure. And now you start going into the cloud, and how secure is the cloud? And you want to operate your system in the cloud. So a lot of challenges there. And of course, in physical, it's just an ever-present. Somebody goes out there and does something stupid with a rifle or a shotgun or whatever, and they've got to be, how far do you go down the road? I've been in countries where every substation had a security guard with a shotgun. I don't know if we're going to go that far. I doubt it. But some of these places are pretty remote. So, but we do have this kind of ongoing challenge that we worry about. So I did talk about the capacity, and here I wanted to kind of show a little bit around what we're seeing as far as growth in solar voltaic and offshore wind, onshore wind, and there's a huge growth. And if you go to the queues in many of the ISO RTOs for generation, a lot of it is more solar, more wind. And of course, as that comes on that system, as they get approved and built, and then trying to manage those with conventional plants and how conventional plants can, kind of work together with the renewable energies, especially to make them successful, help them be successful, and also enable us to get carbon out of the system. And of course, just kind of give you a little bit more about what's in the queues here. And the hybrid is with it's really kind of a solar battery type thing. And many of you, I'm sure, have heard of the duck curve. This is a thing that happens. I don't know why my computer talks to me once in a while, but somehow Siri's is on, and I'm going to turn them off when I find it. But basically, this is all about the ramps and what's going on the system. Is the sun's coming off, and you got to be able to back that up. And sometimes it comes off really quick. And so you either got to start ramping your machines up sooner, or battery storage, or other designs. And so we're seeing that exacerbated over the years. And of course, this just gives you an idea what solar production looks like, or wind, compared to, let's say, what your expectation would be on a set of megawatts. And this is something you can manage regulation, and manage. But if it's all by itself, on average, how do you manage it a little bit harder? So you're going to need something to kind of slip into those valleys there and keep it steady. It's kind of an idea of what we've been seeing with inverters. And this plays in a lot with also large loads. Large loads are inverter-based resources. Solar, wind, load. It's asynchronous. It's like a large generator. It's just a negative generator. And they have large inverter complexes. And what we have seen with inverters is their behavior was, I'll say, disappointing. We had to kind of catch up on it. Where in California there was a blue cut fire where inverters during a single line to ground fault, we lost 1,500 megawatts of inverter-based resources just like that. They just cease to operate, and then they wait for a while and they come back on again, which again would also be it's hard to manage as it's coming off. So this idea of riding through events became very important, and we've now written some standards for that. But that's for new ones, but for the existing panels, there's still a worry. Another thing that we've been seeing with inverter-based resources has been that they don't necessarily provide an ability to absorb or provide reactive power as much as they could. In other words, they're really tightly banded based on what the manufacturer puts them at. And what we learned in Spain is you need to open them up. They need to be able to support voltage with reactive power, either absorbing it or providing voltage or VARs. And that was one of the fundamental failures in Spain. So we were kind of chasing that down with existing inverters, asking them to change that. And we can do that. We have some approaches we use with organizations with alerts and what have you, ask them to make some changes. But of course, what we see here in this particular case in Texas, similar type problem where they almost got to their maximum single contingency, which would be very serious. There was a certain level you simply don't want to get to. You're getting close to your under voltage and under frequency load shedding, and just a massive overreaction to a simple line to ground fault. They're working on this. They fixed some of this because we wrote standards, and some of they were able to, take the grandfather off and ask them to work with their existing controllers and improve them. I did mention this one already, which is the 60 gigawatts that was generating on the order of 300 megawatts. And of course, if you use effective load carrying capability or some of the other measures, you'll miss it. So you need to do those hour by hour analysis, and you got to look at different scenarios now. It's much more scenario planning than it is working for the peak. If you can handle a peak, you can handle anything else. Even if it's peak on the shoulders, you can handle anything else. That no longer holds. You need to really do the detailed analysis. This gives you an idea of how important natural gas is to our fleet right now. And as I mentioned before, there is a concern about how gas and electric work together. They don't always play nice. It's getting better, but again, there's no rules in the road for reliability when it comes to the gas industry. It's not like the they need to start winterizing their wellheads so they can take the cold. They need to winterize their processing plants and compressor stations. New York City almost ran out of gas during Elliott. That'd have been a disaster if they didn't have any gas in New York City. And I'm not just talking about power plants, I'm talking about heating and all the things that gas is used for in the city. They would still be lighting pilot lights now if that had happened. It was very close. So I think it's something you have to, we're continuing to work together with that industry, and seeing some progress there. Did want to talk about we're seeing some of the tight areas in North America. This is a 2025. I should have had the 2026, which just came out. It's even more red on it. And then the reason why is simply this: you're growing more, but you're not building enough. And if you're replacing 400 megawatts of coal, it's a lot more megawatts in solar and wind to replace it, and batteries to replace that. And so we are seeing kind of a decrease in actual capacity, even though we're seeing an increase in load. I'd say that 3% increase is low. It's higher than that now. It's on the order of 5. So obviously, as I mentioned before, we need to kind of work on our gas electric interface. Again, it's another, interface that really creates an interconnection of energy systems. When you lose a large nuclear plant, you have to ramp up your gas plants to make up the difference, but there's a worry that the pipelines may not be big enough to accept that ramp because they weren't built for that. They were built to provide gas to homes and factories they don't have that kind of profile. They don't have reserve gas. They'll pack it as much as they can, but there's just so much they can do there. And then, of course, we have solutions. So we're really kind of working our way into this world of distributed, decarbonized, and digitized system, the 3Ds. And this is really this idea of how the system is transforming from where it was to where it's going to go, and how do we manage that change rather than do it in a kind of I'll call it more chaotic way. The change needs to be managed, and so that means that we need to understand the implications when we take a unit out that we're replacing it with. We have to develop sufficient transmission. It's hard to build anything in this country, in the United States. You can't build a gas pipeline. Hard to build a transmission line. The consumer's just not thrilled about seeing. I stop my car and I take pictures of transmission lines. Right? There's not many people that do that. They don't like to see them rather than they weren't there. But they are a critical part of energy delivery. Making sure that we have a fleet of robust balancing generation that can offset some of the ups and downs of the generation, be it longer term or regular, short term, and understand where your energy is coming from 2 weeks ahead, 1 day ahead. Again, you didn't used to have to worry about that because if you had a 400 megawatt plant, you're going to get 400 megawatts. But if with cold weather and you got to know where your gas is coming from, you talk to the guys in Iceland, New England, they don't know where their gas is coming. They're watching for ships out in the ocean because they've got a liquefied natural gas facility there to bring in gas from that's liquefied to offset the impacts of cold weather. So they're spending a lot of time understanding how much oil do I have in the dual fuel, how much is can I count on from the ocean that's coming in from Algeria or wherever, and through the liquefied natural gas, and then how much I got in the pipeline. So again, it's got to understand what's that going to be short term, operation reliability perspective, operation reliability, and then long term, when you build a system, we need to understand what are some of those limitations. So we're writing some standards in that arena as well. And then the states need to kind of step forward too and make sure that they're building the right level. Because according to the Power Act, we NERC cannot order, nor can order the construction of transmission or generating capacity. I feel like I can regulate energy, the output of generation, but I can't. So you got to build it. That's a state decision, and it's generally paid for by the public. So we got to do all of this while we're seeing lots of load growing on the system, and we've been really kind of reviewing this growth to understand what are the implications, and again, it comes back to the equation I was talking about before, which it comes back to what's reliability and how is it defined? It's defined with adequacy. Do I have enough? And operational reliability. We used to call it stability or security, excuse me, but the cyber guys stole it, so we call it operational reliability. And that's really around, again, voltage, current, frequency response, ramping, all that operations stuff. And so we're actually having a challenge in both parts of that equation. When we start talking about the kind of load growth that's being anticipated here. And even if it's like, they'll build their own generation, then the question is, are they connected to the system or not? Are they just ring fenced and they're off on their own as an island? Well, then that's one thing, who cares? But if they're connected to the grid, they're still getting support from the grid. Via, again, the frequency I was talking about, the stiffness of the grid through the spinning mass, what have you. So how do we manage that interconnection? So again, do we have enough megawatts? Well, it's hard to build. There are some folks that have been using some of the powers of the federal government to keep certain coal plants open for longer periods of time. And again, the wisdom of that one can go back and forth on. But it's very hard to build and to get gas turbines once, even if you get permitting to build. I think GE's pretty much their queues filled for the next couple of years at a minimum. So how do we get the megawatts we need? And I will call it actually megawatt hours we need. And then once we are connected, then what's the challenge of how they act when they're connected to the grid? And what I mean by that is, what does the wavefront look like? The energy wavefront that they're using. What does that do to the system? Are you going to be exciting natural frequencies of the system and have a worry about oscillation, small signal stability, natural frequencies? Or are you going to be creating stress on transformers? Are there power quality components or harmonics components to this wavefront? So how does it act when it's operating? And then second, how does it operate when it's under stress? For example, an event on the system, a line to ground fault. And in this case, for a large load in Dominion, 1,700 megawatts, what happened was that as usual, you got relays that are looking at that fault and opening and closing. And there's a period of time that it does that. And basically 3 strikes and you're out. I close in 3 times and then I open up completely because it's a sustained fault. Well, the large load was looking at these voltage depressors and saying, well, that's it then. I'm getting out of here because I got to preserve my refrigeration or my cooling for my site. And so they just disconnected 1,700 megawatts and went to their backup generators and kept running. So the load went away, even though it's still running. And then, of course, that shook up the system a bit. And we had a similar event happen later on. And they're working on solutions around maybe opening up the timer so that they don't come off as quick during normal fault clearing. Or do they just reduce the amount? In other words, instead of going 3 strikes, go 2 strikes and you're out. So there's a host of different solutions that they're looking at. And then we've seen similar type of issues with cryptocurrency in Texas, where just about anything that happens on the system, because they're very sensitive to price and to the system conditions, they'll just come off. And again, sometimes you don't want them to come off because that spins up your system. It's the opposite of losing a generator, right? Where frequency goes down. Now you got frequency going up. And all of our standards are set for a loss of generation, loss of load, but small amounts of load compared to that. And I mean, 1,000 megawatts, 2,000 megawatts, San Francisco goes away, right? Or Chicago goes away. But these are single point. So those are some of the challenges. It's, as I like to stress to my large load colleagues, extremely important load that we need to be serving, critical for our e-commerce and our AI, but we need to do it in a way that's wise. We need to understand what the wavefronts are and how to design the factories so that they don't impact the grid. Maybe they can have on-site storage or what other solutions, filtering, or other solutions might be necessary. And then also they need to care about what's happening with the other large nearby, because what happens with that large load impacts them, and it could create a control challenge as well. So how do you manage those controls? How do you design those controls to be supportive of the grid and supportive of the loads working together rather than fighting each other? And this is nothing new. We know how to do this stuff, but some of it's more challenging in the sense that we have to change the way in which we design the system. We have to use new tools, new types of tools. We may need to maybe we can simplify some things, but right now we've got standards going in place that says you have to have three-phase models for your inverter-based resources, and will be valid for what you've got there. You need to be able to use them for studies. When it comes to energy, we are leading the way in doing energy analysis rather than capacity analysis. I used to do the long 1 day in 10 stuff when I was working with Roy Billington and the crew and composite reliability with transmission and generation. But now we have much more scenario planning. What's the worst day look like? What's the worst day I'm designed for? And what's the worst day that I'm going to be seeing in the next couple of weeks? And how do I make sure that I'm ready with my energy needs? Again, it's changing the way in which we think about the power system and how we design that system. So I think there's more challenges in this area of stability and oscillation than we've seen before. I've talked to my colleagues in the UK, and what they're seeing is every time they get an upgrade, it sounds familiar on your computer, right? Whenever you get an upgrade from Microsoft, something weird happens, right? It doesn't operate exactly the way. There's always another bug, another patch. And they actually do the same thing with their inverter-based resources. They upload new software for their control systems. And when they do that, it creates potential for oscillations on the grid. And so they've been monitoring the grid, identifying what's causing those oscillations, go back and find the offending inverters and making sure that they get tuned right. We have much more of a tuning requirement now than we ever had in the past. And that's why I tell folks that we're really going from the largest machine that man ever built. That's what Steinmetz said, I believe, to the largest computer that we've ever built, where we have a lot more solid state power electronics. We imagine a power electronic breaker. It moves much faster than a breaker now, which takes about 3.32 seconds to operate a breaker. Now we can go much quicker. A transformer that could be solid state. Maybe we get away from the magnetics altogether. Maybe we go to DC. Every transformer now is unique. If you had one that was power electronic driven. You just drop it in and it will figure out what it needs to do, and then boom, you're on your way. So there are certainly many mechanical changes potentially occurring on the grid, as well as then just the way in which we think about how we manage that grid. Should we just eliminate the Eastern interconnection to have even much smaller interconnections with back-to-back DC ties? Is that the way forward? So I think, one's imagination is our limit. And as we start thinking about AI and the large data centers, we become dependent on that AI to help us run the system. It becomes a critical load that we cannot run the system without, potentially, just like we can't run the system without gas now. So more on that, who knows what that'll look like in a couple of years. But right now we have a workshop, as I mentioned, to Rudy tomorrow and the day after, where we bring together the large load companies, power companies, and working quickly together to identify all of the potential risks and how do we manage those risks, probably through standards, so that we can get some consistency in design and ride through capability. We look at performance and how can we bring them to the collaborative table to help us write the standards that we're going to be following. So I think it's an exciting time to be in the business for sure. We're seeing huge growth, new technology implementations, and I'm trying to hang around a few more years longer to see what happens. So with that, I'm kind of happy at this point to take any kind of questions that might be out there. I know I've kind of covered a lot of ground, but I'm trying to make sure I had a feel for where we've been, how we got here, and maybe where we're going.
Thank you, Mark. So Q&A, as I mentioned before, I start off with the students having first dibs on questions. So students, please unmute yourself, introduce yourself, and ask Mark the question that you have in your mind. Students?
I have a question. First of all, thank you for the presentation. I thought it was really interesting. So I have a question related to large loads and reliability, because it's also very closely related to my capstone. So, and I wrote it down. Large loads, such as data centers, generally prioritize reliable service over things like emissions reduction, mitigating load. In your opinion, what is the single most effective solution to move being able to prioritize these other issues for, such as behind the meter generation, transmission infrastructure updates, or other things?
Well, that's a good question. And, I think that, again, the U.S. is a weird and wonderful place. And one of the weird and wonderful things about the United States is we really don't have a consistent policy, a federal policy. That ends up kind of being more of a state by state policy. So at least we have at least 50, if not more, policies. So what happens then, of course, is you have one president who writes a bunch of EOs, executive orders, and everybody goes running that way. And then the new president comes in and he cancels all those EOs and writes a new ones. So people are trying to figure out, how do I run that way? And it becomes a it creates a lot of uncertainty in investment, for sure. Where should I be investing? If I start building a gas turbine, and 4 years from now, another administration comes in and says, we will not run gas turbines anymore, or any ones in construction you can't use anymore, then it's going to be stranded investment. And of course, there are people that work at these companies, and they go home, and their kids are telling them, well, Dad, you work for that dirty gas industry. How could you possibly do that, right? So, I mean, there's a real kind of back and forth here within the country. I don't think that everybody has the final solution. So I think to a point about weighing which ones, it comes down to a number of things. That three-legged stool I mentioned before, which is the affordability, the environmental impact, and the reliability. Those three things. which ones are going to get you to where you want to be? Where is that balance, and what does that look like? I have challenged my colleagues in certain parts of the industry to show me how this power system can run with no mass. And I think it can with batteries, synchronous condensers, hydro. But how do you design that system and what does it look like? Can we get there and support the load that we're talking about with renewable energies and long-term storage, and only for emergencies, maybe have a backup diesel or natural gas or whatever. How does that look? How do we design it? And what tools we need to design that system? So I think the Capstone project sounds really interesting, and how you are going to be able to manage the balance between those three trilemma, it's called, legs, and depending on the natural resources you have available to you and their characteristics, your solution could be different, right? If you were in Norway, you have nuclear plants and hydro, you're done. You've got reliability, you've got environmental clean. Now you got to make sure you build a few more dams. Not everybody likes a dam, shockingly. I've seen them built. They're really cool engineering, but I can see why people don't want them in their backyard or don't want to give up their land for hydro. But the point is, each one of these has this kind of balance, right? They can coal out of the ground, taking gas out of the ground, using wind and solar. They all have their characteristics and how you try to get to that fine balance. So I don't have a solution for you. I'm a reliability guy, and I want to make sure I have enough energy to serve energy needs, given the policies that we're dealing with. And every state has a different policy, which is really hard to build a system around that because of the interconnection. It's all in the same boat. And federal policy is inconsistent. So it creates a lot of uncertainty. PJM has been trying to get their generation markets to work, and they have been having a heck of a time attracting investment because of the uncertainties from an investor point of view. And so there are even a lot of renewable energies that have been approved, but they can't get built because either can't get panels or the equation for economics has changed without tax credits and all that. So, I don't know if I answered your question, but it's because it's a hard one to answer. But I think having a discussion around weighting of those and then looking at the different solutions you might get, we use a linear program or whatever else you want to do, but there probably maybe faster ways of doing it to kind of get to equilibrium based on certain policy decisions. Might be interesting.
Thank you.
Okay. Question for Mark?
Yeah, I have one.
Go ahead. Please introduce yourself.
All right. Thank you, Mark, for a great presentation. My name is Panache. I'm also an energy systems engineering student. So I get that we are talking about resource adequacy, and there are the metrics that we take into consideration, like the loss of load expectation, the loss of load probability, and the EUE. So my question is like, what are the considerations that we take into account with these variables on a higher level in terms of the regulations or the guidelines that the NERC take into consideration or that they look at?
Yeah. Well, 1 in 10 came from a paper that a guy named Wichhorn wrote in 1947, where he basically said, 1 in 8, 1 in 10, maybe 1 in 10 provide acceptable reliability based on the statistical analysis. And he and Calabrese, who's another guy that was around that time, were going back and forth. And I'll never forget one. Back in the day, and it wasn't that long ago, when you wrote a paper, somebody could write a comment on the paper, and then you'd respond to the comments. That's lost now. We don't do that anymore. But those comments and discussions were really important. And back in the day, Calabrese I was asked by Witchhorn, should you include emergency procedures like reducing voltage and all that when you do your calculations of 1 and 10 and your loss of load expectation? And Calabrese said, no, unless you want to be always operating in emergency conditions, which is actually, quite wise. And that's why we didn't include a lot of that, except maybe sustained demand response or energy efficiency that we knew we could count on in our loss of load expectations. And of course, we did 1 day in 10. Why? Because in the 1960s, we didn't have a lot of storage. We had daily peaks. That's what we could do. And we figured within 24 hours, machines would be back online. So let's not worry about it. Let's just look for one event, 1 day, they used to say one event in 10 years, when we stack up all the generation and we have independent forced outages that would take one plant out, put another plant out, another plant out. So probability times probability, right? No common mode. And then if you got below load, boom, one event in 10 years. That world's changed. And it's changed because at any hour, depending on the scenario, the weather conditions, and also, by the way, what's happening this hour depends on what happened last hour. Now you have an hourly calculation requirement because we're no longer capacity constrained. We are energy constrained. That is to say, we are fuel constrained and many of those resources, even if it's gas, if you have to deal with some of the cold weather challenges we've been facing. Happens also sometimes in our weather. So, and it's now a common mode too, right? It's like the common mode being the weather. It's not blowing. I have smoke in the air from wildfires, and therefore my production is down 80% on my solar panels. So I need to understand what the implications of those events are. Some of them sound wild and crazy, some not. And then what do we design to? We design 8 days of smoke-filled air or 5 days of smoke-filled air. What are kind of the design parameters? And there are folks who've been struggling with this. We, of course, at NERC have been, we actually developed a metric. We call it a normalized expected uncertain energy. We didn't develop it, we use it. And we went to a number of 0.002 or 20 parts per million of total energy produced in a year would be kind of like the cutoff. If you're above that, 0.003, 0.004, you're less reliable. You're below it, you're reliable. And we got that number by looking at what's going on in Australia. In Australia, I think it's an AEMO report, where they have a design basis for Australia. And those, of course, the states in the east, which Perth is all by itself over there. And they design to this level, and then they monitor that, and they come back and do the calculations again. Because so you also have a lot of base load units too still around, so if they use them, they use the solar. So they came to a new kind of metric to design the system to, and they monitor that design. And we have been using that in our long-term reliability assessment. Again, 2025 or 26, which is released here. It's on our website, long-term reliability assessment, LTRA, and we talk about using normalized. So that way, the main difference, which interconnection you're in, and the total energy that you produce will be different depending on where you are and how big your system is, but normalized to 20 parts per million per year is what we're kind of designing to. And we use a different set of tools, hour by hour calculations. You can use Monte Carlo if you want. You got to play with different scenarios of what are you really wanting to show? For example, if Uri was the worst we've ever had, we want to design to Uri. Is that going to be the level that we designed to? And so we're still kind of playing with some of those kind of scenarios. And the scenario in Montana will be different than the scenario in Florida. So what does that look like? So a lot of work going on in that area. And we basically put a number out there and said, show us when we're wrong. Just like when I started in 2007, we said 15% reserve margin, because that was for thermal systems and 10% for hydro. If yours is different, give me a different number. Otherwise, that's what we're going to say. Below 15%, you're in trouble. Below 10% on hydro, you're in trouble as far as reserve margins. And that was a rule of thumb. Again, I got no thumbs lift that we used back when I was in MAP. We got your power pole. Does that get to your question?
Panache?
Yeah,
Look
thank
up
you.
that
Thank you.
Look up that
Thank you.
Witchburn paper. It's not people, and then people know that that's where it came from. And then in about 1969, 68, PGM said after the blackout, we're going to use that now to design our system. And then people like Jim Robinson did that for years.
All right. Thank you, Mark.
David Ellis has his hands up. So David, go ahead with your question, David.
Okay, thank you. Just a question about inverters and what inverter functionality or what inverter operating modes are not being used today that you'd like to see available.
Yeah, thank you. David, you kind of got to step back and figure out, well, okay, what do these big machines give me? And when I take the big machines off, what do I need to substitute it with? For example, frequency response was buttressed by inertia of the machines. Well, rather than having that, can we use batteries and fast injection of energy, right? So sitting back and saying, well, no, what do I need it to be doing? I need it to be damping the system, right? And there are inverters that can provide power damping. Again, nobody's building those in the system, or maybe they have the capability, but they're not turned on. In Spain, we learned that the regulator had said, I want you to run all your solar to unity power factor. You cannot go outside. So then when they needed the reactive power support, absorbing and providing reactive support, it wasn't available. And they weren't spinning a lot of machines. And by the way, they were exporting a lot to France. And also they had oscillations that were bugging them on their system. And so, which of course, if they had power dampers, they probably wouldn't have had. But I understand it was the force oscillations actually coming from an inverter. So I think an ability to provide absorb reactive power, an ability to offset ramps, and then finally an ability to provide frequency. As you know, all the inverters we're putting on our system right now are following the frequency, they're following the leader. And when that frequency gets weak, they start coming off, right? And you need something to create frequency. And it's not clear to me yet if we can, again, build that system so that the whole interconnection from Minneapolis to Tallahassee, from Portland, Maine to New Orleans would be on the same frequency if we use grid forming inverters on, let's say, storage facilities. But certainly we need that ability to provide frequency. So that would also shore up the system and strengthen the system that we're weakening. They call it like system strength, that short circuit stuff. So I see that being another component. Damping, offsetting ramps, voltage support, frequency. Everything that you used to get from a spinning machine, other than megawatts, we need to be able to provide some sort of substitution for. And I think inverters could do a lot of that. We might also want to think about synchronous condensers or some other technologies too, if it makes sense to support it. But anyway, that's a great question. Did I help, David? Good stuff.
Yeah, he's nodding his head, Mark.
Yeah, I saw that.
Yeah. Well, I have Jim Robinson has a question for you.
Oh God, I can't believe that. I learned everything I know from Jim Robinson.
Good to see you again, Mark.
It is good to see you.
Mark, one of the things you said today especially triggered some thought to me that we're in an energy 24/7 market now. The concept we used to have when I was in the business was we're always shooting for enough controllable capacity to hit that 1 day in 10 mark. The world has changed. I'm beginning to think that since our inverter-based load and generation is so variable, and we have quite a few perturbations that we can control but many that we cannot, I actually think we're better to go with a model of what is the variable demand on the system. The variable demand that's on the system is customer load variations plus inverter-based variable demands and generation. You get a net of the two variables. We could attempt to fast control frequency using battery storage devices and other fast response to take care of those risks we face today of suddenly losing 10% of the wind or some malfunction that we have a voltage fault and it takes off 5,000 megawatts of load.
Yeah.
I think we're better to get away from looking at our variable generation as a generator and look at it as a demand side market improvement that just subtract the two every moment of the day, subtract the two and follow that net variable demand, which has all the perturbations that you talked about today, including frequency control. That I think that's going to become our new target to trying to maintain the market. I'll give you an example. PJM, the last 2 years of PJM solar data, if you go through that hour by hour, there's been 15 events where they've had a solar drought for 40 hours in a row, 40 consecutive hours. You have to have a way of dealing with these things on weather-based equipment. You have to be able to get through a solar drought. You have to be able to get through a wind event where the wind gets to a Beaufort Force 7, which is just about at the same spot. It's not a hurricane, it's not a tropical storm, but a Beaufort Force 7 wind will shut down all the wind plants.
Yeah.
It's about 60 miles an hour
Yeah.
is the point when they all shut down. That's similar type of cliff that we've dealt with for years. When the frequency goes down to 57.5 hertz, all the steam units are going to trip due to turbine issues.
Yeah.
So I think we do have to get away from a capacity driven to a variable fast response energy market day.
That's interesting. I have to give that some thought. See it how the design of the system would change. You're absolutely right. The BESS is a very helpful. I think I mentioned the Texas event where the Permian Basin and the western part of the state and the eastern part of the state and Louisiana, they froze up in the last cold spell. And in Texas, they were saved by the storage that they had available. But it wasn't 2 weeks. It was only needed for a day or two, and they were able to kind of get through the challenge. And then we saw the Wyoming event where some of the batteries actually helped reduce the drop from the event and offset the nadir because they had only basically variable generation, inverter-based resources in Wyoming, they're either solar or wind, but that battery helped there too. So maybe you have to step back and say, what does that design really look like? How do I manage the variability of the system and create some certainty around that? And clearly storage is going to be a critical part of it. The Spanish system had 10 megawatts of storage, and you go to California, and you're near almost 100,000 megawatts, right? So and we're going to actually work with California to see, well, what happened in Spain? Did that happen in California? Or what is the difference there? But to kind of come back and say, well, what am I going to design to? And can I offset it with battery storage or other types of technology? There's a new technology in your neck of the woods called form engineering or FE, and it's actually using iron. And as iron corrodes, it releases electrons. The payback is twice, so you have to put twice as much back in. But when you need them, like 96 hours, who cares if it takes you 2 weeks to recharge it again if you need it for those 96 hours? So there's some new technologies that folks are working on too that will be helpful as well. And I think, what does the toolkit look like? Do we use some of the same tools we have now, or do we have to change them so we can do the kind of analysis you're talking about? So just kind of a variable load market with some sort of technology, batteries, rather offsetting the valleys. Of course, then that's the Dunkelflauten on one side. The Germans always got this stuff right, and then the Hellweiss, which has got too much. Well, that's easier to deal with. Just turn them off. But the Dunkelflauten is the one we really worry about the most.
Yeah, I actually think, Mark, that if we can get the battery technology to work at a very high maximum capacity for a very short time, maybe 4 hours max, but very high, I think that can replace inertia pickup,
Yeah,
droop due to speed governor control,
yeah,
and all those things that need to happen very quickly to control
Yeah.
frequency that do not
Yeah.
come from the balancing authority.
yeah. And put grid forming inverters on there so that reduce frequency.
Yeah.
Maybe
And those batteries would be autonomous. They would just measure frequency and damp out the frequency swings, but you have to have them extremely high megawatt capacity, but not too much energy storage. You wouldn't build them for 30 hours or 40 hours of energy storage.
For that. I like it. Let me think about that some more. Like
Yeah, variable net generation. I think variable net generation is the way to look at it. Just add the variable solar and wind against the demand by customers, and we meet a new target called variable net demand.
Yeah, got it. I've challenged Tesla to show me the system that does it. Maybe I'll rope you in.
Yep. Good to see you again, Mark.
Good to see you too, Jim.
Yep.
All right. Thank you, Jim and Mark. Tom Kissinger's got a long, eloquent question and comments. Hey, Tom, if you're still with us, why don't you read it?
I see him there. He went with his player. I see this.
You're here? Tom?
Hi, yeah, I'm here. I'll just try to summarize quickly, but basically my question was, is there room for NERC to implement some regulations for inverter-based generation? Because inverter-based generation doesn't really, for what you've been discussing and for specifically the protection system, doesn't really respond in the way that the grid, would expect from a traditional generator. And essentially all of our protection systems depend on sequence currents and certain threshold level of higher magnitudes for fault currents and so forth. And there's really not anything in place right now to sort of recreate that, even if we go down the route of the better battery storage systems. And obviously battery storage systems are going to ultimately need inverters to integrate with the ESE grid. So I'm just wondering if there's room. IEEE has put together like the 2800 standard, which does kind of put some of that focus there. But at this point, I'm wondering if we maybe need to have some pressure put on at the regulator level to kind of ensure that these inverter-based resources are gonna sort of continue to allow the grid to perform as it had, if that makes sense.
Oh, absolutely. And we have a number of committees that report into our board, and one of them is called the Reliability Security Technical Committee. And underneath it, there's a working group called the Inverter-Based Resource Performance Working Group, IBRPWG. I don't know where we get all these things. And they've been kind of cracking this for quite a while. And ultimately, FERC ordered, FERC can do this. They ordered us to write standards on ride-through and modeling, because we found that a lot of models that one has do not represent what's in the field. The challenge there is, you get in the queue 5 years ago, 3 years ago, and then they finally do the study, and you're you cleared the study, and then you go out to the market to buy your inverters, and they've all changed, right? I mean, the technology moves so quickly nowadays compared to a spinning turbine. And so how do you get good models? Are they user-defined models or are they generic models? And then when it came to 1547, 2800, we used a lot of that information in the standards that this recently got approved by FERC. It's called 901. It's got the order number 901. And we used them, but some of it we couldn't because it wasn't easy to audit compliance. And we also found that many of the manufacturers that were in the meeting were kind of carving stuff out for themselves. We did run into an issue with one organization said, well, I haven't built my HVDC line yet, but when I do, I will not be able to follow the standard because I've already bought the equipment. So it's like, whoa, okay, got to deal with that one. But overall, we've been trying to address that through regulation. Here's the challenge, though, Tom, is that you can't necessarily go to an existing plant and say you got to change. Not all of them can. So going forward, we have a lot of rights and capability we've asked for, and will be a new solar plants. Existing ones, we're going back to them and asking them to open up their VAR capability to ride through. We send a number of alerts out. We have 3 levels of alerts. One is information. Second is information, but also recommendation. Third is you got to do this. And when we went well with our third, many of them said, "Thank you for telling me that, but I don't know if I'm going to change or not." And they don't understand that they don't have a. No, you have to change. So we're working with existing facilities as well. There are cases where it's not possible because the technologies they have are so old that they can't adjust. But we are working on this problem through a NERC set of standards. I ask you to look at the FERC ruling that just came out, I think it was last week, Thursday, on what they call the 901 activities. And we're continuing to work on those, again, beyond just modeling, but trying to get to ride through curves and also I think we're looking at frequency support and all that. So we're trying to get there with our standards, and it's a real challenge. It's very technical, and not many people in the industry understand how this all works. So it's been a fast track over the last 2 to 3 years. And of course, the standards, they take a long time. 2800 took how many years? 1547 to open it up took a number of years, and now finally with the standards, now there's a period of time it takes for people to actually start following them. It could be like 6 months, a year. We're looking at how we can speed up our standards process so we can go at the speed of risk, we would say. So we're staying in front of it. Like with large loads, we're trying to get in front of that with working with the large loads. But anyway, take a look at those standards. Again, we're performance-based generally. So this is the expected performance. How you get there, that's going to be on you. You being the generator, owner, and operator. But we've addressed some of these with the standards. So it's a good question, Tom. And I wish we would move faster than we did. The first time we saw an event was in 2017, and everybody thought that was a California problem. Nobody weren't going to see this much solar. Come on. And then we started seeing it in Texas. Folks said, wait a second. And now it's Texas. And then they started seeing it in North Carolina. So then it started getting folks got to run. I think with large loads, though, I think there's a lot of people pitching in at the same time. So hopefully we'll stay in front of that. Because it'll be the same set of challenges, right, Tom? Ride through, voltage support. What are the models? How do I model this in my software package? Do I have a good model? Et cetera. So, hopefully that gets to your question. Thank you for asking.
Okay, there's a question from in the chat box, but DC Chapley,
I can look for it.
if you're still there, could you articulate your question? Okay, any thoughts as to why aren't more mechanical spinning inertia devices being installed?
Yeah, that's a good question, and I think NERC has standards in place where we measure frequency response. Jim's probably well aware of this. And we try to look at certain key events and try to make sure that we have enough frequency response within the interconnection to support the system. And so far, we haven't had a lot of issues because there seems to still be enough oomph in the system. We continue to monitor that. That will certainly set the bells off because there's a standard that says that you have to keep it within a certain level. That frequency responses have a certain kind of capability. And frequency response is how we measure this inertia, mechanical energy. So again, something we continue to monitor. And the question is, should we be generic and simply say, you know what, from now on, all storage devices should have grid forming capability, power damping capability, and high speed energy. Should we just say that from now on? And so that's still, I think, a work in progress. But right now, it appears that we have enough on the system, even without the retirements. There are certain areas that are getting weaker. Certainly in PJM, where they've had a lot of plants retiring or projected to retire, is an area we're concerned about because the further away you are from that mechanical energy, the more chance you have of having some challenges. And of course, how they're replacing that? Are they putting in battery storage, et cetera? So there are standards in the books that they need to meet, and that will help drive technology applications, I think.
Okay. Time for one or two last questions for Mark. Anybody?
I think Jim has his hand up again, Rudy.
He never took it down.
I also have a question.
Yeah.
Question? Okay.
You mentioned earlier, and this was maybe just like a one-off, but in Texas, when there was cold events, batteries stopped working, and I know batteries are kind of often referred to as like the saving grace for turning renewables or variable generation into firm load. Is batteries not being able to work, is that just a function of their mechanics, or is that just their nascent nature?
I just misspoke. What I was trying to emphasize is they saved the day.
Mm-hmm.
That the gas on the west part of the state, there's a lot of wellheads there. They use a lot of water, and you can winterize it, but it costs money. So some folks make a bet and say, "I'm not going to winterize." Also, on east side of Texas in Louisiana, again, there's a lot of wellheads there, and they also froze. You kind of look up, I think, what's the name of that company? McKinsey has a report out, and they show how much really huge reduction in gas production there was during the cold weather. But what saved the day was the amount of storage that Texas had built. And they had built it for a number of reasons. Part of it is because, especially in West Texas, it's sparsely populated, but you have to have a lot of gas load there. So storage helps keep it secure and stable in that area. But it was also saved the day because when the gas went away, just like what could have happened with wind or solar, the battery was there to save it. Now, it wouldn't have maybe lasted 2 weeks, but they were storing when they could and then offloading when they had to. And it was a very important resource during the recent cold spell we had this winter. So look at the McKinsey gas study and see what happened there. And then what we've heard is that it was the storage facilities that they call bulk electric storage systems, BESS, that really helped save the day for Texas in this last cold event. So I'm sorry if it sounded like I said it didn't save the day.
Okay, no, that makes sense. Thank you.
Well, thank you again, Mark. This is an excellent presentation and excellent Q&A. And there's a lot of important, interesting information.
That's some great questions, for sure. Yeah.
So
thank you, Rudy, for inviting me to this.
I think Jim did have his hand up because I put it down and he put it back up again. So
all right, Jim.
I didn't want to ignore him before we cut off.
Sorry.
The only other thing I thought I had was on this topic. when we look at what is referred to in the industry as area control error, which is the formula created a long time ago, that particular formula does look at variable net demand only. It does not include variable solar or variable wind because they're not controllable. So the formula really looks at just variable net demand. So ESE is already following the wave. If we somehow can tie very reliable, high storage, high output devices to control ESE, I think that's a way to make up for some of these uncertainties on how well the solid state inverters are going to work. Thank you very much, Mark. It's stimulating discussion today.
It really was. I really appreciate the opportunity. And thank you for inviting me, Rudy. It's great to see you again as well. And really appreciate the questions from your students and participants. Really head scratchers. And,
thank you again, Mark. Yeah. And just to, Jim is in our advisory council, so it's all of, so be really
you're lucky. You're lucky to have NERC, as well as he was out studies. So I mean, we've seen it all.
Thanks a lot, Mark, and thanks a lot, all of you. We will have our the series will continue next week. We'll have a speaker from EPRI talking about, this is a great title, Power for AI and AI for Power. So they will.
Oh my God, those guys from EPRI, you got to watch out for them. I agree.
Yeah. Well, we'll see you next week then, all of you.
Take care, everybody.
Bye bye.
Thank you.
Bye-bye.
Thank you.
Thanks, everyone.
Thank you.